So later the lecture.
Yeah.
6 students are out of 20.
Hopefully still has lots available. Yeah, I already have like a rough idea of what I'm doing. Hopefully you can give some details into like which areas to work on. It is hard.
You can go and get
I pay you to do the dissertation on
I found one place where they can do the dissertation and they have and as you can, they can check for the playing areas, they can check the right
you do the dissertation for you. But if it hits the purpose, then the degree is not yours. Yeah, it is kind. But I know it's a painful process.
So for it, just for you.
Don't tell me this thing, David. Don't tell me about this. Like, it's a learning process.
That's why I pay 17,000 pounds
To be here, right?
to be here and learn. So he doesn't want to know histories and for a year of pay for
I'm not so much concerned about the process, but it's like this knowledge you get while you're doing it, that's important. For some people, the degree is just a piece of paper. That's why they pay the money to do it. I need the degree.
That means
So for me, it's
I also want to get
some students just written short like this. I don't know how to do the calculation.
yeah, no, it was like a rehearsal, it wasn't a real. It was like a drill. Yeah. So I don't know why they do the drill this time of the morning.
Don't tell me. You don't give up.
Like a drill, like a
because I don't know.
It is.
no, I don't say.
I think
Of course, I would rather go and travel to
because I was diagram, so once that you
very long. Yeah.
Yes, knowledge.
do you just set it now?
If I had so many kids too, I have no money. All your money invested in the children.
Because yesterday class was too hard. Because I write on paper. But you couldn't hear very well. What's your result the last one? How did I win?
How was that one?
Your day?
Day? Yesterday, I
Still,
you remember you told me what
The one.
what else communication?
Yeah.
I'm just reading some pieces and
Charges.
yes. Like how much of presentation do you expect? First class?
Thinking of
I don't guarantee this sound.
Something familiar.
Why you should pay for 2 points? You simply do something, I think you can get around 2 points. 2 points is one, just 50%.
So he's coming after the gym.
Because he should have done from 100 to
Did he see you? Yeah, of course. He showed me like this. I said, come inside. Was it walk? Which is wrong? Walk. Mr. Sorry. Yeah. The street ends towards the university. You have a road crossing. Then you don't cross, you take a right. His gym is there, I think. Because the gym, from where he was working here, I was inside. And I told him when he came inside. So he said he's going back to the gym. Yeah. And his family will be here soon. Yeah, I told him. So you're going to carry them.
I can't go back and
Where is it,
learning the names just for
Do you have the minister?
I have one of those. Sorry?
Yeah. I forgot to buy. I will buy it from. Yeah, but more.
Личные проблемы немного.
No one writes.
It's a habit, isn't it? When you sign something can work, you have to take off your date.
he wants to be special.
It's to work, it's the work. It's a good habit. You're not in office anymore, man. It's school.
It stays with us till we go into the.
Okay guys, in the very end of this lecture, I need to correct something because in last lecture, in my teaching materials, I made a mistake. If you go to slide 8, we have something at the red bottom, and in last lecture, it was the angular speed is r pi over t multiplied by kg, but it was wrong because it should be equal sign. Okay, and I have uploaded the corrected one. Okay, and another thing is because this expression is from some theoretical basis, and you can today I give you some tables, and you can just find the expressions in your table, and in your calculation you can just use that. Okay.
In the exams, will you use this page?
Sorry?
In the exams, will you give you?
Yeah, this one is for your exam.
Okay.
Yeah.
So
I
we
got
can
this
use
from
it.
last year.
We can use this.
Yeah, yeah, yeah. And in your future works, if you need to do some estimation for the wave force or something, I'm sure you can find the table somewhere. So we just use it. So after we know the expression for regular waves, we can estimate some forces acting on the floating structures. So today we will have 3 or 4 examples to tell you how to estimate the wave forces on structure and how to get the motions based on the forces. Okay, but before that, I would like to show you a very short video. It's from a CFD simulation. So in this structure system, you can see we have 4 mooring lines, and we have 4 columns, and we have maybe 2 or 4 pontons. So you can see that if we assume the wave is a regular wave and we have only one, you will have the structure motion like this. And if we consider the problem is a 2-dimensional problem, your motion will be in this way, right, by the waves. And in the meantime, you also have heaves. If you don't have this mooring line, you can feel the motion in z direction. And in this problem, we also have the motion in x direction. So of course, if we assume that it's a linear system, after we know the wave expression, we should be able to estimate the forces on that. And of course, after you have the force, if you can estimate the weight, we know that we have the second Newton law, and here is the motion, right? But of course, in the examples today and in the lecture today, we are doing estimations. So it means we will simplify many things, but not like in the simulation by computer. We can get the pressure and the forces in a very high accurate level. So if we look at this video again, I think you can feel that the motion is like something connected by a spring, right? Because after you print out the force plotting, the force will be like this. And it's like when you have a greater distance, you have greater force. So it's very like we are connected to a spring. And we know that in water, if you do a ship resistance test, the resistance will be a function of velocity, right? We know that, and we can use this resistance curve to estimate the power you need from your propulsion system. But whatever, it will be the force, or I use R for resistance force, will be a function of V, right? It's very like it's connected to another thing, and we call that a damper. And they have different features to provide different forces. Like the first one, if we have a stiffness coefficient, the force will be something like you have the coefficient and you have the distance. You can estimate the force from this spring, right? And from the damper, it's about the speed. If we have another coefficient, actually we can estimate the force, but this time it's not distance, it's speed. We need to do the differential operation to over time. If we have another source term for force, we can give another function, but it could be 0, right? But anyway, we can build up the equation for the whole system. We have the weight, we have the acceleration, and we have force, right? Here is this radical basis, and then we can create a new equation to include all the factors in this system. If in a system, in this slide, we can see a simplified equation. So if in this system, we don't have this additional source term, it's 0. And we don't have this damper, C is 0, and this term is 0. So actually we can have motion equation in this way, right? If you have a new constant, and we use different symbols for that, but anyway, we can give another equation to some cases if you don't have damper, or your velocity is very small. We can assume it's 0 because the equation will be simplified and the solution will be simplified. So in this case, obviously, we can solve what is z, right? Because we have only one unknown variable. And the solution will be here. I don't think you need to know the procedure about how to get this solution, because you can always find a table like the one in your head. But last night I did something to get the final solution. Like from the very beginning, we have this equation, and according to the mathematical rules, finally we can have something here, the expression for z, the distance or the motion distance. And you can see that we have a constant here, we have a phase angle here, we have another constant here to control the motion amplitude. But anyway, you can see that if we go to the slide, it's in this form, right? And if you look at my solution carefully, you can see that the constant for the time, we call that natural frequency or natural angle speed. It's here, and you can find that from your table. So you see, it's here, constant for your time, and then it's for the conclusion here. Okay. And then according to the definition for wave period, it should be r pi over the angular speed, or r pi over the frequency. After you know the natural frequency, we can know the natural period, right? It's over there. So to this system, you can see that if we know the mass, if we know the stiffness coefficient, actually after we know the wave, we will know the motion features of the whole system, and you can just apply the expression here as long as you have a good table. In some systems, if the damping force cannot be simplified, we may have an equation in this way, right? We have a spring, we have a damper, you have the mass, the weight, and you have the acceleration, you have motion, right? So actually, if we have equation in this way, you can see that again we have only one unknown variable, is z, is the motion distance, and of course obviously we can solve this equation, and probably it's not very easy, but I'm sure you can solve this based on your mathematical knowledge. And in English I think it's called it's homogeneous differential equation. Right? Because it's homogeneous because we have no additional term on the right hand side. If we have anything, it will be homogeneous differential equation. And in this slide, because I got this from Professor Longbin, so you will see the results straightforward. But again, last night I also did something to solve this equation. I used more than 4 hours last night to get this. And because now this system is a bit more complex, you see that? Because we have the differential operations twice and one time, and also we have the original form. So actually, according to the different values of C, we may have different solutions. And basically, if we just look at this equation, we may have 4 possible solutions. The first one is, of course, C may be 0, so we can just go to the previous slide. It means we don't have this damper. And so see, in my calculation, if C is 0, we can go to the previous one. But if C is not 0, we still have 3 different possible solutions, and they will present different motion features. Like when C square over m square is 4k over m, if in your calculation everything is correct, and I'm confused there. Oh, here. The final solution is like this. We have some constants, but we do have an expression, and I can show you the final result is a constant, another constant, time, exponential, something like this. But anyway, from the expression, you can see that for this system, yes, you have waves acting on that, but actually, if you have a disturbance to your system, you can see that with the time of the change of time, you don't have oscillations, right? Because we don't have sine function or cosine function in this expression. So, go with time, you will go to the middle slowly, and here is the theoretical basis. We don't have oscillations. If C square over m square is smaller than 4k over m, again we can solve this equation, and the final result will be here. It looks like a very complex expression, but if you look at this expression carefully, you can see that actually it's a cosine function, right? So after, in this expression, after you have a disturbance, you will have oscillations. And then, because we have a constant in this way, the oscillation will be smaller and smaller, go with time, right? If C square over m square is greater than 4k over m, again, I use another 10 minutes to get the result. Another expression, And you can see that this time, in this case, we don't have oscillations again, and the expressions will be here. After you have a disturbance to your system, again, the structure will go back to middle position slowly. Probably, in this case, it has a different speed, like in this one. They are different, but they don't have oscillations. We have oscillations only in this case. Okay? It depends on the design of your structure, because you can see that when we try to find out the criteria, they all about the system, like the system weight, like the, what is K? Oh, it's about wave, the wave number, and C is the damping coefficient. It's also about the interaction between your structure and the water, right? So based on the expressions in this part, we will know that if you know the weather conditions in an area, and if you can assume that in this area the wave is a regular wave, in some cases we can assume that if you have a good design, actually we can control the motion or the oscillation of your structure. Probably sometimes it's in this case, sometimes it's in this case, but in most cases we can control that. For example, we want to control in this area, we can give a good M, right? Because we can control the weight of your structure by your design. So in this lecture or in this module, you don't have to understand how to get the results in this way, because you have some tables, right? But if you are interested, you can do the same thing like I did in last night.
Seriously?
Yeah.
It depends.
So you see that in this slide from Professor Longbin, he told me we have 3 situations, but actually it's not include this one. We have 1, 2, 3, because we want to have a good system to include every factor we can imagine in our calculation. And then here is a very special one, and it's a very typical one. If in your expression you have a sine function, the oscillation will be like this. After you push it, it will oscillate. And then over time, the oscillation will be smaller and smaller, and then go to zero again. Okay? In a very practical cases, obviously we have weight, we may have damper, we may have spring, and we have waves impacting on that again and again with time, right? So from the very beginning, we have Kz, we have I did something last night, and you know that we can have the expression for z as long as you have equation in this way. And I also did something last night for this one, and you can see that we can have an expression. Oh, sorry. 3 expressions for different cases, but anyway, we can have an expression for Z. But obviously, in practical engineering, if we have waves or some other additional source terms go with time, we assume that in this way. So you can see that now is a non-homogeneous differential equation. Actually, for this one, we also have the expressions, but it's really difficult to get the expression by handwriting, so I didn't do that last night. We just use the expression in your table, okay? But we should know that when we look at this expression, here is weight, here is acceleration, here is damping constant, and here is stiffness coefficient, and here is distance, here is velocity, right? And here is external force, like from wind, from wave, or something else. And please remember that this one is a complex system, but we do have the expression for Z. Z is something with probably X, in this case it's Z and time. And you can find some expressions. Okay, if we assume that is heave motion, you can go to page 3. And the motion response is presented by equation 30. Okay. If everything goes well, you will have an expression like that. And then in our calculation, you can just use it. By this point, I would like to ask you a question. In the first slide, you can see a short video, and the structure is connected to some mooring lines. And of course, if we have heel motion, it will be tensed, and then you have, it's like a spring, and you have a force to get it back. But how about this? If we don't have mooring lines, can we assume K is 0? You have heel motions. Why? It's still like a spring. So from the compression between the two cases, you can see that it's still like a spring, right? And the spring force is from buoyancy. Because if you have a structure, it's just floating in this way, sometimes it could be like this at T1, but at T2, it may be like this. So in this case, the buoyancy volume is here, and probably, it's very likely, the buoyancy is greater than G. And in this case, the buoyancy volume is here, and it's very likely it's smaller than G. So if you print a plotting, it still change with your distance, right? But again, if you have a submarine underwater and you have waves in this way, you want to get the response in X direction. Do you have spring force? No, right? But you do have damping force, because when you increase your speed, you have a greater resistance from the front part. Okay. So okay, you can see from this slide, I give you the expressions for the heave motion. And of course you can find from your table, so I don't need to go through again. But if you look at this expression, we can put some terms into a container, right? It's like a container, and we can present it in a easier way. It's at 0/k times q, and if you have an expression for wave or something else. And this q, you can find the expression. It will be 1/√² 1 minus omega nature omega square 2 damping ratio and a square. Here is Q, and Q should be included in the expression for heel motion or horizontal motion. But anyway, according to the expression Q, you can see that this term, of course, could be 0, could be greater than 0, but obviously it's larger than 0, right? But in this part, it may change. And then the natural frequency actually is from your design. So you can see that by control your design, you can control the Q, and then you can control the motion, right? So here is the reason why. Oh, here it is. Here's the reason why when we design our structure, we try to avoid the area here, because you can see that if my natural frequency is very close to the frequency of waves, here will be 1, right, or very close to 1, I mean the value. So this part will be very close to 0. It means this part will be small, and this part will be a greater value, right? So when you calculate the motion, the motion will be greater. Obviously to your structure is not okay, and to your course members on that is not okay. They will vomit every day.
So this is motion response, yeah?
Yes. In page 3, you can see that here is the expression for Z. But actually, this expression could be used for other motions in X direction and Y direction. But in the expression, the F will be different. Okay? And to a ship or to a floating structure, we always say that we have 6-degree motion or 6-degree freedom motion. And here in this slide, I can show you the 6 motions or 6 freedom. We call them the heave, surge, and sway. Where is it? Here. Sorry, I show you next slide. So I think this one is better, right? We have 6-degree freedom. And if you don't have any mooring lines, you're just floating on open water. Your ship maybe have motion in 6 ways. And when we try to find out the motion of your structures, our theoretical basis is F and A. But because for A, we may have 6 directions, and they have completely different motion features. So actually, we need to build up a matrix to include all the 6-degree freedom. And then we need a sequence. And in this slide, I show you this sequence. Probably sometimes you see x1, x2, x3, or x11, x12, but it's always between 1 and 6. Here is the reason, and here is the sequence, okay? After you see the index here, you will see the equation is for maybe this one, or this one, okay? Because they have a sequence and they have index number. Okay, the last point in this lecture have you heard about added mass?
Yeah.
Added mass, or sometimes we call that virtual mass. When you calculate the motion of your structure or something. I think you should have something from other modules, like from the lectures delivered by Professor Longbin, or something like advanced hydrodynamics or something. When we do our estimations in this way, if we have this equation, we can solve the expression for motion, right? When we use this way for your estimation, we have a criteria. Like last time you asked me, if we say we use Morrison equation for small structures, how to define small or big, it's here. Okay, we have a criteria. If the wave height over wavelength is smaller than 0.2 and the structure characteristic length over wavelength is smaller than 0.2, we can do the estimation in this way. And here is the criteria to define the structure is big or small to the wave. Okay, but whatever. When they use this way to estimate the motion, and here is the theoretical basis, but actually for floating structures we don't use this math. We also have added mass, and here is the acceleration, and here is the real force we need to consider, and obviously it's greater than the force from the classical expression. Okay, so this time now it's like we have a pressure force, and we also have a part for added mass. And for the reason, that is because if you have anything in water, when you want to go forward, it's like you need to push some water away, or it's like you bring some water together with you because you have friction. But anyway, it's not yourself. You go with some water. This added mass is for that part, and because we can't see that, but we need to include this factor, so sometimes we consider this as a virtual mass. Okay, so in a good calculation we need to include this part, otherwise sometimes to some structures it could be huge. Okay, so to include this factor, it will make your calculation to have a better safety level or safety margin. Can I have a break? Yeah.
Mr. Monk, so what it actually means when the mass M, which is the mass, is the mass of the water coming towards the structure. So what it actually means is it is not the actual mass that is coming up to the structure as an added small mass.
Yes, but it depends on the direction of your structure, because from the table you can see that. If you have a pillar and you go in this way, here is water. You do the estimation for added mass in this way. But if your structure is deep stuff moving in this way, here is another estimation. Yeah. So it depends on the direction, and sometimes you have different estimations on different rules. But you do need to include that factor.
No matter the design of the structure, even if it's this one.
Rather than just reading.
Yeah, it depends.
It's better to understand when you're solving something rather than
There also pneumatics, hydraulics, mechanical, and last part second unit was the electrical systems. We'll study about electrical systems, hydraulics, mechanical, electrical, you have these three. What are the differences?
What if you go through, like what examples using this equation solution?
how you provide
in next lecture.
So the rework examples to show the application. We don't have the notes, so we don't know what to expect.
We'll use 2 or 3 examples to let you know roughly how to use the table.
Correct, because the theory part is like very
Yeah, obviously, if you just know something like the expression, you will be confused.
Okay, there will be examples.
Thanks.
And then you can the layman The question is what will you study or who will you study?
Korean food is good, quite spicy. Going to die. Is it very spicy? Yeah, it looks like cuttlefish, right?
I was about to take a shower, and then
He's got a
that time in the morning. You wanna try this? I lost 10 minutes of my life waiting outside.
Can you eat it? Yes. Are you like hitting it? It destroys it. It's really bad. In Singapore, this is
There is someone who like this kind of
there's no taste, man. It's like your Your mouth is there. Yeah, it's like you haven't checked the little pot, like you put it in your mouth, you put your lips. But yeah, after it goes in the stomach is it's challenging. It's a young people's food kind of thing.
Okay, guys, can I start?
Yeah, it's a challenge. But some young people in this world yes. This is called negative peer pressure.
So, after we have the expression for your waves, we should be able to estimate the pressure on that. And if you go to the table 1.1 and the expression for pressure at bottom, you can see that we can divide the pressure from waves to, we can divide the pressure from water to two parts. The first part, you can see that it's just rho g, rho gh or rho gz in this expression. So we can see that is we may know that 20 years ago we call that static pressure, right? And the second part, it looks like complex, and this part is, we call that dynamic pressure, and this part is to generate the motion. Okay, and you can see that in this expression we have a cosine function, so it will go with location, will go with time. So if you have a floating structure and if you have a wave, you will always see the motion like that, because the force acting on that is in this way. Okay. In this table, another point is in the second bottom line, you can see acceleration is du over dt. So from this expression, you will see that it's the acceleration in x direction, right? Because we usually we use u, v, w to present the velocity in 3 different directions. If we do the differential operation to the small u over time, obviously we have the acceleration in x direction. But you may say that in this table it's not a full one because we don't have a z. For example, if we consider a 2-dimensional case, here is x, here is z. Here is okay for the calculation for the surge, right? Going forward and backward. But for heave, we really need to know a z. But you cannot find that from this table. But don't worry, because in this table you can see the velocity potential here. Right, if you look at the expression from bottom 1 to 3, right? Expression for phi, and phi is the velocity potential for the velocity, the general velocity. I think you should know what is potential velocity or velocity potential, right? In this area. If you don't, you can go to any wave theory books and have a look. I got this page from Wiki, and you can see that after we know pi, the potential, and we do the differential operations in different directions, we will know the velocity in 3 directions. Here is for u, here is for v, here is for w. If we put them together in 3 directions, we will have the general velocity of something. Okay, so it means if we know the potential function here, we can get any of them, because you can do differential operation for, in the x direction, it will be u, right? If you do the differential operation in y direction, it will be v. It's this part. And obviously, we can also do in another direction. In that case, we got u, v, w. If you have a point in a space, put them together with directions, you will have velocity with direction. Okay. But anyway, in this table, we have the potential function. It means you can have the velocity in any directions. So, here is the expression. In this table, here is the expression for velocity potential. And in this table, we know what is u, but we don't know what is v, right? So if you want to know the velocity v in y direction or z direction, we can do differential operation in this way. And then, according to the expression here, we will know that it's k I h k t e k z think you can have an expression like this. If you know the potential function, you will know the velocity. Okay? And you can see that the form here, the format here is very like the expression for u, but if you look at them carefully, they are different. Okay? And then in this table, you have u, you have du over dt is for a, right? In x direction. In this case, we call that surge, right? You go forward and backward. From here, we know that, we also know v, the velocity in this direction, because we can get from the potential velocity. And obviously, after you have the expression for v, we can do differential operation over time, and then it will be az, right? So it means after you know this function, we will know velocity, we will know the acceleration. In this table, you have the expression for them only, but actually you can calculate by hand for another direction. Okay? We may use them in our following examples. So, as we know, today, if we want to estimate the motion of a structure, of course, we use some numerical software like you can use CSAM, you can use StarCCM or CFX, and when you try to find out the motion, we need to know the weight, and it's very easy to get that because you know your design. And we also need to estimate the force on that, on your structure, and it's from water or from waves, right? When we do this, if we have a pillar, we know that at different parts, they may have different pressures acting on that from water. So if we can know the force on a very small element, we can do a surface integration for all the surface, and then the final result will be the force with the direction, right? That's the reason why you can see the expression here. We have pressure, we have directions, and we do the integration for all the surface. Okay, and behind that, you can see we have an expression for pressure, and this expression you can find from your table again. Okay, so it means if you have a good handbook, you can do the estimations, or you can do the simulations in your software. But the truth is, when you use the numerical software, it could be time consuming. If you have a good structure, you may need about 1 month or 10 months just to build up the model. And after you have the model, you need to create some numerical cells to put into that space, and then you can solve the governing equations. Then you have the force, you have the motion. But in our preliminary design, obviously we can't use 2 months or half a year to get the model. So we can use some estimations if you can meet the requirements like this, if your structure is small, if the wave height is small, we can just use the equations given in that table. And for example, the expression for acceleration is here. And here is for surge, here is for heave. For all of them, you can get from this table. Okay? And in our cases, we always assume that we calculate the structure for deep water. It means in our expressions, if here is the water depth from seabed, we don't have any influence from the seabed because the water depth is quite high. So you can see that in the final expression, we have nothing to do with the water depth. Okay, we just don't use it. But in this table, you can see some expressions for the cases in shallow water or in intermediate depth water. You can see that we do have another factor, that is water depth, because in shallow water you have the influence from seabed because the water depth is too small. Okay? But in our cases, in our examples, we don't use that. We assume the water depth is quite high. We don't use D. Okay? That's the reason why you can see the expressions in this way. Okay, now after you know the acceleration of a water particle and you know the density of this water particle, so just to this area, if we have a very small length element, just to this area, how to get the impacting force? Am I right? Am I right? Just for this cross-sectional area, I can write in this way. It's like your water particle has an acceleration. Is here. You have your area. If I have a small length element, here is the force on this part, right? If I do an integration, it will be the force to the whole structure. So here is the basis, and we can use this expression to do the estimation for the force acting on that. Okay. So after we understand this, we can do some examples. Like in this slide, we want to know the vertical dynamic wave pressure forces acting on this pontoon. I know some wave features, like the wave height is 6 meters, the frequency or angular speed is 0.6 radius per second, and I also know the wave number is omega over g, because it's deep water is here. So now I want to know the vertical dynamic pressure acting on this horizontal pillar. And we know that from the previous slide. We know that we will have the expression for the acceleration in z direction. Okay? So that means if we have the mass, if we have the z, actually we know the force, right? So from your table, I think you can have this expression. And for the mass, in water we know the displacement of this structure. It means as long as we know the size of this structure, we know the displacement, and it will be rho water multiplied by the volume, right? So if we do an integration from this end to this end, we will know the total force on that, right? So in this example, you will see the calculation in this way. I don't think I have time to go through, but you can have a look after this lecture, okay? If your calculation is correct, the final result will be here. The unit is kilonewton. And you can see that the pressure is always changing, the dynamic pressure. And sometimes it's to upward, sometimes it's to downward. Now we may have another structure. This time we have big plate and we have a pillar on that. Here's the wave. This time I want to know the force, but it's the first step, and based on the force I want to know the resulting motions. In this case, I tell you that I have additional force. The force term is here. It means you can apply the expression in page 3. If you go to the motion equation with the index 29, you can see that it's just this case. And then it means you can apply the motion response in equation 30. We know what is we know the expression. But before that, we know in this expression we have a force. It means we need to find out the force first, right? And for dynamic force, if you want to generate the heave motion, it will be like this, right? Do we have any force on this pillar from waves? Yes or no? Where is it? Because when you calculate, when you do the integration, the pressure on this surface is to this way. The pressure to this surface is to that way. They don't generate heave. And for the force on this surface, they don't even have this surface, because it's connected to the base, right? So actually we just need to focus on the heave motion or the force on this base, okay? And when you do the calculation, you have force on this plate. But please remember that the area of this place is like this. Okay? And the area, if in calculation, it should be 4 pi d1 over d2. Oh, sorry, minus d2. In this way, for your calculation, okay? And the force, dynamic force on this area, the bottom area will be 4 pi d1 square, or it's d1 or d2?
D2 right now. So it's going to be D2 minus D1.
Okay? So because you have the difference here, it means you will generate the motion. And in the estimation, you can see that actually we don't do the integration. We just assume that the pressure will be all the same, like the pressure on this point. It will simplify our calculation. And because we know that the structure is small and the wavelength is quite big, so because of the change here, and here will be very small. So it means we can just use the pressure here to generate this motion. So you can see that we just use x is 0 to do the estimation, and it will be quite simple. On the top, we have this pressure. On the bottom, we have this pressure. Put them together. Here is the total force for your heave motion. Okay, and after that, we have the pressure of the force here already, and according to your table, you can calculate what is K. It's in equation 26. Okay, we call that hydrostatic stiffness. For the natural frequency, it's in equation 27. Okay, so you can see that if we have a good table, we can solve this problem for the estimation. And for the mass or the weight, here is the weight of your structure. And of course, we know that we need to add another part. We call that added mass. And in your table, the last page, oh sorry, not last page, page 4. In your page 4, you have two equations to estimate the added mass, but actually they are for different motions. If we have a pillar, here is the diameter, and it's moving in this way, we will use this part to push the water. And you can see that the added mass estimation will be cubic. It's for this case. But if the pillar, the motion is in this way, we assume that the added mass is exactly the same like the mass of the structure. So you can see that in some cases it could be huge, more than thousands tons. So in this case, it's for heave motion. So we will use the first one to estimate the added mass. That's the reason why you can see a calculation. Oh, it's here. Okay. And again, in this case, we have a structure like this. So when you push the water, the area is here. So that's why you can see two parts, right? So after you have everything, put them together, and we apply the expression for Z, for heave motion, you will see that here is the here is the expression, if my calculation is correct. So you can see that we have a cosine function, but we have the amplitude here. So it means in this case, the motion will be smaller than 0.85 meters. Okay? If here is 0, here is 0.5, here is minus 0.5. So the total motion will be smaller than 1.7 meters. So by an estimation in this way, you can calculate the maximum motion of your structure just before your design, after you know roughly what is the size of your structure, right? But of course, if you do another simulation by your numerical software, the result could be completely different because we have much more details of your structure, and I'm sure they will be different. But in the beginning of your design, this one is very helpful.
In the mass that we're calculating here, the first mass, the hem, we added the mass of both the small column and the larger column. But when we're calculating the added mass, we did a subtraction. I don't understand. Why is it addition and again subtraction?
When you have motion in this way,
Okay.
you push water away, right, by this surface.
Mhm.
But in water, you have water here, you have water here, but you don't have water here because you have a pillar.
Okay.
It means you don't use this part.
Mhm.
You need to minus that part.
For the addition, for the added mass, right?
For added mass, just for added mass.
But for the total mass, it has to be the addition, right? Because that's what I'm seeing right on the mass there.
Can you come to me after this lecture because I
Okay.
didn't follow you.
Oh, okay. No problem.
Sorry. And okay, in example 3, if we have a column like this and we have wave going in this way, and I tell you the wave features here, the wave height is 5 meters and the frequency is 0.3, and I also give you the expression for the motion is here. So again, it means you can apply the expressions in this table, right? But this time, I need to know the surge motion, am I right? Surge forces and surge response. So this time, when we try to find out the force on that, to generate the surge motion, I should get the force on this surface and the force on this surface, right? Because the force on this surface will not generate surge. I just need two forces on the two ends. That's the reason why you can see the expressions here. The total force will be the force on left-hand side plus the force on right-hand side. Because we have expressions in that table, we can just carry on the calculation and find out the final expression here. But by this format, you can see that if I have a good design, I can make it 0, right? If L K over 2 is n pi, the sine function will be 0, right? For the wave number, we know we will get that by r pi over lambda. Here is your wavelength. And L is your design. It means if L is n lambda, the force will be very small, and it could be 0 in some cases. It means the motion could be 0, right? So from this example, you can see that if you know the weather conditions or the wave conditions in some area, you can design based on that, and you can control the motion. Here is the basis. Okay. And then, I think in this example, it was told that the damping ratio is 0 because it will simplify the calculation. After you know the damping ratio is 0, it means the damping coefficient is 0, right? And because the motion is in this way, we don't have something like a spring, right?
Okay.
Because we talked about that in the first lecture. It means K is 0, right? So in this expression, we can simplify the motion equation. And then we know that up in the final solution, the motion will be in this way because it should be periodical, right? And we can assume the maximum amplitude, and we use the frequency here. And then you can have the first differential result, second differential result, put them together back. We can solve this expression. The final result will be here. Again, you can see that we can estimate the maximum motion distance is 1.9 meters. Could be positive, could be negative. So if after this estimation, we will know that it will just move around in this area, right? You can go through the 3 examples after this lecture, and actually we have another one, but I think I can leave this to next lecture or to the final review for this module, because sometimes in your final exam you can see this. So yeah, so I think I can finish this this lecture today.
Dr. Monk, I just
Yeah.
wanted to confirm the other time. It's not as if I was confused. I just wanted to confirm. So what we're actually saying is for the total mass, the weak mass.
Sorry, can you use
So
another one?
I'm
It's fine,
sorry,
it's
I'm
fine.
sorry. So for the big mass, we're actually adding the mass of this, which is the area multiplied by the density, and then the mass of this, the area of the density, right?
Now you are talking about the
Addition.
weight estimation. For the weight, for the real weight of that structure, of course you need to include everything.
Everything.
Yeah, of course everything. But for added mass, it's not.
Because it's only the surface of the one here that is pushing
Yeah.
it off. The other
Yes.
one here is already at
Yes,
above.
it's in water already,
Oh, okay.
so you don't have the surface to push water.
Yeah, it's only the surface that is pushing
Yeah.
the water. The other
So
one is at.
after your calculation to include all the surface is wrong because this surface is
It's
not
not
working.
there,
Yeah,
yes,
yeah, that's what I mean. Oh, by the way, do you know we have a job event in next week? I think it's next Friday. You know that?
Are they going to hire someone?
Sorry?
Are they going to hire someone?
I'm preparing my CV. But I think you can just talk to them. And in previous years, they go with their CV. I don't think they will sign the contract in next week, but I think you can give them a good impression. For this part, because in this lecture we have two parts from Mia and Wen Xian, but for waves, I think if you I think you can download something from our university.
시험 나올 거 지금 그 상황 그대로 나와. 성우한테 물어봐가 당연히 이거 준호한테 물어봐야겠다. 지금 시험이에요.
메테리얼에 들어있어요. 작년 거.
이렇게 나갔어.
This one is very good because you can see that all the expressions. Yeah, you can see that it's actually quality. But actually from internet you can have many reference books like this. Yeah, I'm not sure whether this is the best, but it's useful to me.
I the definition of editness. I wonder about the definition of editness. What's the exact definition about
Because in Chinese we call that additionalness, and in English we call that additionalness, but I don't know how you call that in your language. Alright.
Maybe my professor used English name.
You can see this from any place related to fluid mechanics. When you go forward, it's like you need to bring some water around you. Right? It means you are high reactor. So now it's not your real weight. It's greater than your real weight. Right?
Is it something related to the wave mechanics?
I don't think so. It's a very easy problem. It's like when you are going forward, your mass is m, right? When you calculate the forces and no problem, right? But you always have water here. When you try to go forward, especially when you have acceleration, it means you push the water away. They have
So this added method.
so when you go forward, you bring them together. It means you go with them. So when you calculate force, like this, and we call this part is added. It's added to your structure.
Something like dynamic term. Whenever
Yes.
it have some kind of acceleration or velocity, something like that.
If you have a constant velocity, you don't have that in there. Once you have acceleration,
Some kind of rigid type.
so you can understand exactly.
From the price.
So that's why you explained during the lecture about my friend asked me about the why extract the section. Because when we moving the middle section not have resistance.
When you have a pillar in water and when you go forward, you use this area to push water. But now you have a pillar and this part is not working.
I see. Okay,
I went to read at least you scared, you forget the food. Oh my god.
presentation 干嘛的？叫 review 吧，叫 literature review， 叫 proposal。你早点写完呗，干嘛拖到 deadline 呀？
对啊，我就说，那我能不能在就是那个之前，然后我真的是有说这个是本月份。
我还没给你写呢，不过那个 proposal 好写，那个 literature review 不好做。
那个是下个学期的。
对，那个不好做。这个 proposal 不用着急，可以给你讲。因为那个就相当于是你的研究计划，你要不懂的话，你现在也没法定。
好啊。
他要求多少分？
我回去
应该是个很短的东西吧？
对。
然后100分，那个没有分是吧？有分吗？
有7%。然后它有一个格式，就给我。
你发给我，你回头发给我。
好。
你们票订好了是吧？
订好了，Francis 刚才发给我了。
12月几号走？3号走，然后11号回来，正好一周。你们在北京住一晚吧？
对。
你陪他好好玩吧。
行，我妹妹正好在北京上班，然后正好能在。
他本来是想直接转机，后来我本来计划送3个人去，然后后来英镑跌了嘛，3个人有点紧张，然后就改2人了，改你们俩以后钱又余付出来点，我就让他最好是在北京玩一宿，因为他没去过。我不是听他说的，我听他们说他特别想去中国吃点狗肉去。
吃点狗肉。
没，他们开玩笑，我就说你们要有机会就带他好好玩一玩，主要就是。
对，是可以好好玩，但是我7号不是有一个那个。
因为像他们这帮人吧，很难得去中国那边一趟，
挺远，
没有什么机会。
好。
青岛也是。
那我有个presentation挺多人，7号，正好在中间。
在那块儿吧，我估计你要做2个 presentation 给他们讲这边的学习工作情况。那那块儿主要是我在这边和他们再联系，反正去也搞不清楚。主要就是一个保证他安全，一个保证他玩好。当然你也要玩好。
哎呦，这 presentation 在中间就有点压力了。
The time this afternoon, I think, from 1 o'clock till 4 o'clock. This afternoon, there's quite a lot of time, so I go to the library to start typing and try and have a look through them. I think some of them written will disappear with the table going into it.
Yes. And even the one, if you're not in security, then you come up with